Hi everyone, I'm just going to quickly go through this problem of the loop. So as you recall, we have a scenario where we have a frictionless loop and we have a car that's going to travel around the loop. At the bottom of the loop, the sum of the forces has to result in the centripetal force. Remember, the centripetal force is a net force. These are the only two forces acting, the reaction force and gravity. So when gravity is pulling down, for us to actually have a result of a centripetal force, the reaction force has to go up and it needs to be much larger. So that size there overcomes gravity and we're left with that centripetal force. At the top of the loop, we have an opposite scenario where the weight force, or the force due to gravity, is providing the centripetal force. And we have a very little or no reaction force at all. When we want to solve a problem to determine what speed would be required to keep a car in the circuit, we solve for when the reaction force is zero, because this represents the threshold, the position where our speed would have to be larger than this particular value. So that's how we solve. At the top, we want to consider the threshold, i.e. that point where it has to be going at least this fast for the car to be able to maintain the circuit. We take the reaction force to be equal to zero, which means that we're left with our centripetal force being provided by the gravitational force. We can then solve that, mv squared on r equaling mg. The masses cancel out. And then we find that v squared equals r times g by multiplying by r on both sides, and that comes up here. And then taking the square root of that, we end up with v is going to be equal to the square root of r times g. Now remember, this speed cannot be smaller than this. This is a threshold speed, so it certainly can be larger, but the speed cannot be smaller than this for our car to make it around the loop. Now we need to think about, well, what will be the speed going into the loop? And for that, we think about the energies involved. So to consider the energies involved, we need to think about the fact that there is gravitational potential energy at the top of the loop, as well as kinetic energy. So we know that it has to have a speed for it to maintain its motion and stay in the circle. And we've calculated what that speed is, but it also has a height at this position. So its total energy is going to be a combination of its kinetic energy, because it's moving, and its gravitational potential energy. So when we look down here, we need to think about the fact that the speed provided at the bottom needs to be enough to climb the height of the loop and give the car the speed that it's required to maintain the loop. So the total energy at the top has to be equal to the total energy at the bottom. And so that means that a half mv squared plus mgh, we can't see that, okay, a half mv squared plus mgh is going to be equal to a half mu squared. So I'm using u to represent the speed going into the loop, so the initial speed at the bottom, and v representing the speed at the top. So remember, the energy at the top is going to be a combination of its speed and its height, mgh. The energy at the bottom is going to be just the fact that it's moving very fast. Again, you can see the masses cancel out all the way through. Then if I multiply through by 2, then we get a line where everything cancels. V squared plus 2gh is going to be equal to u squared. So if I then want to solve to identify what speed does it need to be going into the loop, I'm going to solve for u. So I take a square root of this side, and I end up with v squared plus 2gh. Now, because we know what v squared was equal to from up above here, we can actually then substitute that in as well, and then we can end up with a relationship which doesn't actually require us to know what the velocity is at the top of the loop at all. We know now that u is going to be equal to the radius times g plus 2 times g times the height, all square rooted, and that should give us the speed required when going into the loop.